Yeah, very interesting topic. We have received some requests from our audience to cover this topic, and here we are with our new webinar. So, thanks for joining us. Choosing the right battery for solar, basically, and so exciting to see participants from across different regions, from diverse applications. And I know that we have installers, homeowners, product users, and energy professionals in this webinar. So welcome to all of you. Today we'll cover the common topic about the solar batteries and explain how to prevent aging and show how EPEVER basically simplifies the decision for reliable and long-lasting solar power. So before we dive into the technical details, let's look at our agenda today. First, we will explore why choosing the right battery is critical for solar setup. After looking into common types of batteries, we will highlight the most common mistakes that we make when applying in solar batteries and how to avoid them basically. And we will look into aging phenomena, which is very important for batteries. And normally the users sometimes overlook these concepts. And next, we will introduce EPEVER Solutions that makes battery selection a bit simple and reliable. And finally, we will wrap this session up with a live Q&A sessions. So, yeah, why actually battery choice matters? Why it's important to choose the right type of the battery for our system. So, when it comes to solar power, the battery really is the heart of the system. So, get it right, and you'll have reliable power, a longer lifespan, better performance, and you'll save yourself a fair bit of money over the years. So let's break it into basically four factors here. A mismatched battery reduces usable energy and efficiency. So if you choose a battery that's not suited to your system or your setup, you lose energy and efficiency. And cost over time, that cheap battery upfront can easily become the most expensive asset of our solar system we have ever owned. So once you factor in maintenance and replacements, you will see that that upfront cost was not actually the main cost for the system. And for the lifespan, we can pick the wrong type and we will shorten the life cycle, meaning that we will be replacing it faster, far faster than we would like. And system reliability, so the right type of the battery will keep our power stable, whether we are off grid or running a hybrid system or whatever. So getting the battery wrong, we could be looking into wasted energy, constant tinkering, and unexpected downtimes in our systems. So, interestingly, studies show that in many solutions, in many standalone hybrid applications, some specific types of batteries last roughly about 2 to 3 times than the other types of the batteries. So, your battery decision is very important in many aspects, in many directions. And yeah, not all the batteries are suitable for all of our applications. And this is what we are going to cover together today. So before we get into performance and common mistakes, aging, etc., let's quickly review the main types of the battery that are used in solar systems. So first, the lead acid batteries, the traditional workhorses. You'll find them in many off-grid and hybrid systems, basically everywhere. Fluid types need regular liquid top-ups, while the sealed AGM or gel versions are lower maintenance, though they still have shorter lifespans. So next we have the lithium-ion batteries. They have become the modern standard, right? So we see them everywhere for both homes and businesses. And live PO4 is especially popular because it's stable, efficient, and lasts for longer than lead acid. So yes, they cost more upfront, of course, in comparison with lead acid, but they save money over the long run with less upkeep costs and more years of service. And finally, we have solid state batteries. Actually, the newcomers, they come with higher energy density and improved safety, but they are still, let's say, in the adoption curve for solar applications. You do not see them too much in today's applications, but they are emerging actually. So with this quick overview, we can dig a little bit deeper into how each performs and what to watch for when choosing the right battery for our system. So the classic lead acid batteries, right? The long time standard for solar storage for decades. So they work through a chemical reaction between the lead plates and the sulfuric acid electrolyte. So during this charge, lead sulfate forms, and then charging simply reverses this project. And in solar, we mostly see two types: fluted, cheaper, but they need regular liquid top-ups, and AGM or gel, sealed, lower maintenance, but a touch more expensive, actually. So why would one choose lead acid? Well, they are affordable, upfront. They're widely available. You can find them everywhere, and they work well in off-grid for our hardware systems. But there are some, let's say, trade-offs. They are heavy, they got a shorter life cycle, and you can only use half of their capacity. We will look into the depths of discharge. So basically, practically, you can use half of their capacity without cutting their lifespan down. And if you go for fluted types, well, maintenance is always there and you need to top up. And these limitations are exactly why many systems are now shifting towards lithium batteries. So lithium batteries have become the go-to choice for residential, commercial, mobile applications, you name it. You know, they offer higher efficiency, longer life, and lighter weight than traditional lead acids. And here in this diagram, you can see how exactly they work. So on the left is the cathode, on the right is the anode, and then electrode in between. And during charging, lithium ions, those small lithium dots, as you can see here, they travel from cathode through the electrolyte to the anode, where they are stored. So these are the ions stored here. So when your system needs power, the process reverses. Ions flow back to cathode, releasing energy to your load, and while electrons, the blue dots, travel through the external circuit to do the work. So what makes this different from lead acid is actually the intercalation process. The ions slot neatly into crystal structure of the electrodes. And this makes lithium batteries far more energy dense, efficient. It allows 80 to 90% usable depths of discharge. You don't have it with lead acids, and remove the heavy liquid acid altogether. So actually, it's the chemistry that brings too much advantages to the lithium batteries. And in case of live PO4, shall we say, the chemistry is exceptionally stable. It delivers long cycle life and a high degree of safety, even in demanding conditions. There are still some risks, but it's far more safe in comparison to lead acid. So the performance-wise, well, of course, we are talking about 90 to 94% of efficiency, up to 6,000 cycles. Well, basically, if you would think about marketing, you can bring even higher numbers here, up to 7,000, 8,000, basically. But we can say they last 6,000 roughly at 80% of discharge, and the ability to use most of energy stored around 90% every day. And all of this comes with no regular maintenance. And of course, again, this is not magic, right? There are limitations. You need to get temperature management, and every pack needs to be protected and balanced in terms of cells. So that's why the choice of brand and the installation and commissioning is really critical for lithium batteries as well. So in terms of applications, One of the real strengths of lithium technology is versatility. It is not confined to one single type of application for solar systems. Here you can see just a few of them. On the water, lithium batteries are keeping burner systems running. On the roads, they're powering RVs and mobile setups. In towns and cities, you'll find them in solar street lights, and in homes. They are there for backup, making sure the lights are stay on and essentials keep running. And for those needing serious capacity, whether for businesses, community project, or a large, shall we say, off-grid home, modular energy storage systems scale the performance up. So you see, it's this flexibility in size, in form, in application that makes the lithium the foundation for so many solar projects nowadays. And now let's turn to solid state batteries, often described as the future of the storage nowadays. So here you see the on it on the left, the cathode on the right, and in between, instead of liquid or gel, you see a solid electrolyte. During charging, lithium ions, the white dots, move through this solid layer from the cathode to anode. And here, while electrons in blue take the external path for powering or charging the system. So when the battery discharger, everything runs in reverse. So what is different actually here? With lead acid, energy is stored through a chemical change in heavy lead plates. Lithium ion, actually they have a liquid lithium electrolyte, giving lighter weight and higher efficiency. But with solid state, actually solid state changes the game. There are no liquids. This means no leakage, greatly reduced fire risk, improved thermal stability, and because the solid electrolyte can be engineered to pack ions more densely, you get higher energy density, more storage in the same footprint, shall we say. So we have launched an interesting video last month about how durable solid state batteries are. I would recommend just watching that on our YouTube channel, and you see the different tests that we perform on a battery, but it's quite reliable and stable, shall we say. So, as promising as they are, well, solid state batteries are still emerging for solar. It means higher initial cost, limited availability, and a supply chain that's well still scaling. And why mention that? Because expectations matters. Today, solid states fits best where safety and energy density justifies the premium. Costs might be higher. So with EPEVER's outlook, we are supporting early stage deployments in scalable backup and modular ESS. So actually, we have products in the market. We have batteries with solid state technology that you can actually purchase today for your applications. So costs will come down eventually, like many other technologies, like many other evolving technologies, as manufacturers matures. But for now, think of solid states as a near-term pilot, but actually, fully commercial, as mentioned, and available for the market. Where do solid-state batteries make the most sense right now? So basically, hybrid commercial and industrial sites, of course. They need compact, fire-resilient storage. We have large-scale backup systems. The thermal stability is there. I mean, and it's not optional, You need to have a safe battery in such setups. It's essential. And well, for microgrids in space-constrained settings, we said that solid-state batteries can be quite dense in capacity. So in an application where every square matters, then we can use solid-state batteries also. And what is next? As production volume grows and costs come down, I think we will see them entering high-density home storage, and even lighter applications in our daily solar applications. So to keep these pictures simple, solid state delivers safety, density, stability, and as availability improves, the cost will come down and we will see them more and more in our applications. So we are talking about selecting the right batteries, right? We have covered lead acid, we have covered lithium and solid states, how they work, how they are different from each other. And if you look into today's market, there is still this question, lead acid vs lithium, and how we can make the right choice for that. So just to make it simple and have a quick glance at it, we can break it down into some factors. Cycle life. Lead acid might give might give 3 to 5 years, but lithium often gives basically 2 to 3 times higher uh, life cycle in comparison to lead acid batteries. So depth of discharge is also important. Lead acid 50%, lithium 80 to 90, efficiency around 70 to 85% for lead acid, and then we have 90 to 95 for lithium batteries. No maintenance for lithium, or low maintenance, shall we say. Um, and the higher upfront for lithium, but often cheaper in long run. And these are basically established facts. We don't develop too long here, but this is also a commonly asked question normally in the market that, okay, do I need to go for lithium or lead acid? And I think with this slide, we summarize and simplify the rule for selection. And now the interesting part, the common mistakes in solar applications and how to avoid them in terms of batteries. So before we talk about the common mistakes, we need to understand a criteria that is called the battery aging. Aging is simply the gradual loss of capacity and performance. And there are two main um, types of aging. One is cycle aging, which happens each time the battery charges and discharges and is worse with deep cycles. So the more you go in depths of discharge, the more you have aging in your system. Then we have another phenomenon, which is called calendar aging. You buy a system, you buy a product in the market, and you just unbox it, and it doesn't work. It doesn't turn on. That is the calendar aging. That product has been in storage for a long period. So calendar aging occurs even while the battery is idle, as I said, as internal chemical reactions slowly reduce capacity. For solar systems, basically, aging matters because it directly impacts how much energy your battery can store, how often you'll need a replacement, and this means how much money you're going to spend in your project. And recognizing the mechanism of aging, I think is very important, and make sure that you do the right commissioning and you do the right choice for your batteries. Okay, so factors driving the battery aging. We still have lead acid batteries here because they are common in the market, and this webinar is meant for a public audience, not only related to our products. So that's why we include lead acid batteries also here. So for lead acid, the biggest issue is the sulfation and stratification when system run at the partial state of charge or are cycled too deeply. And if you add heat, you will speed up the positive grid corrosion and water loss. In cold weather, you simply get less usable capacity. So you get faster wear. So for lithium ion, it's slightly different. Life BO4, basically in our context. Over the time, the SEI layer thickens. Then we have classic calendar aging, driven by temperature and state of charge. and you can push hard charging in the cold or at the high SOC, and you'll risk lithium plating, and this steals cyclable lithium and raises impedance in your system. So deep cycling and high temperatures also guide the chemistry for lithium batteries along the wrong paths. So DOD and heat management really matters. So depths of discharge and temperature management is so crucial for lithium batteries aging. And for solid states, so the architecture is different, and we have basically then different issues here. So over time, you can see interfacial resistance creeping up, or mechanical voids and micro cracks as electrodes breeze in and out, shall we say. And under high current density, dendrites can still find their way through defects. And like all chemicals, there is a temperature window. So too low and ionic conductivity falls. So you have lower capacity. And also some materials are moisture sensitive. So packaging and integration of the batteries are also the key. And these are the phenomenon that contribute to aging of the battery. So in short, we need to manage the state of charge. The comfort is important, but the more depths of discharge means a lower life cycle. Temperature, we need to control it. And we need to also choose the settings that suits the chemistry that we are applying. You see, the aging mechanism is different for lead acid, for lithium, for solid state. So the charging settings must be accordingly set it up carefully to that specific type of battery. And again, that's where we have BMS, the battery management system, and good commissioning that are the critical points for higher life cycles. So we talked about the depths of discharge. Also, the more you drain the battery, the lower lifespan you have, and the charge rate curves. Notice how, shall we say, high current discharge and the run much sooner for you. And we also see the effect of the temperature here. Cold robs the capacity. That's evident. And heat also shortens the life. So there is a trade-off. We always aim for that middle band to keep the performance steady. So in a sense, in regards to aging, we need to get the DOD, charge rate, and temperature right, and then we will extend our battery life. Now, the mistakes that accelerate battery aging. So, of course, it could be many types of mistakes in battery applications, right? Wrong wiring and etc. But we are trying to focus on the concept of aging here and the environmental factors and what we can do in long run for our batteries. Undersizing or deep over discharge, we talked about it too many times today. This triggers sulfation in lead acid. This triggers lithium plating in lithium ion batteries. And we also have the high rate fast charging. And of course, this adds heat and speeds up the SEI growth. Fast charging and discharging also contributes to shorter lifespan. The poor temperature management, improper ventilation. We talked about the role of temperature, so that's important. And these are the mistakes. So we put the batteries into a very harsh environment, either very cold and or they're very warm, when we still do not change our consumption, etc. We do not adapt it, and then we have shorter lifespan. And we also have storage issues. Storing batteries fully charged for long periods promotes chemical reactions that lead to calendar age. So you might have a solar setup that you actually do not use that, and your batteries are essentially fully charged, but this is called the idle condition. Chemical reactions are there, they are contributing to aging of the battery. So mild consumption all the time is good. And I have some people in remote locations that have programmed their charge controller just to start a load during the night, a small load that prevents idle condition for the batteries. So yeah, I'm not sure if that's suitable for all the applications, but it is recommended in remote locations that you actually do not touch the system and system has no usage for a long period. Skipping maintenance, as I said, mainly for lead acid batteries. Rapid cycling or overuse, we talked about it. Using mismatched components, you can have a charge controller or a system that doesn't suit your batteries or stresses your solar power, stresses your batteries or your system, and your settings are not right. So the cutoff charging voltages and these kind of things are not right for your batteries. So having these settings and matched components are also fine. Nowadays, we are shifting towards hybrid systems, all-in-one systems, and these mismatched components are heavily reduced, but we have still enough customized systems, especially for marine and RV applications, that we build them, and sometimes we overlook how to configure those systems for our applications, and then aging happens. And improper ventilation or placements. This is also a contributing factor, specifically in terms of thermal management. So these two slides, I think, cover in terms of rapid aging, the common mistakes that we have in solar applications or our batteries. So special note about the temperature, because temperature is a critical factor in battery life. We repeated that a lot, but we are going to cover that again. So during charging and discharging, batteries generate heat. If this heat is not managed, it is accelerating aging, and in extreme cases can lead to thermal runaway, a chain reaction of self-heating and chemical breakdown. So to prevent this, good thermal management is essential. Ventilation, proper spacing, and heat sinks. If you are running in a very harsh environment, etc., you need to think about ventilation, making some proper temperature management systems, and also the heat sink with the metal casing batteries that helps to reduce this environmental factor. And that's exactly why our batteries at EPEVER come with smart BMS temperature monitoring. Some of them with metal cases. We can trigger shutdown before damage occurs, and this will protect the batteries. So temperature is very important in our projects for solar applications. And beyond the obvious mistakes, of course, there are lesser known errors that silently kill the batteries. So mixing old and new batteries, it's a common mistake. We talked about it enough, and there are enough information about it. We need to avoid mixing old and new batteries because their capacities are different. We are creating sometimes unbalanced series and parallel packs. Of course, we need to avoid them. We can use an incorrect charging profile. We need to avoid it. Sometimes the battery comes with the BMS, but we ignore using that, or and even if it's in place and we are using it, we ignore the BMS alerts, and these are showing the problems in our systems that occur regularly in the system. So we need to monitor the system and see what went wrong in terms of BMS alerts, and is there anything that we can use to prevent issues for the future. So if we want to connect everything we have learned together about aging and mistakes, batteries will age naturally due to cycle and calendar aging, but user mistakes accelerates this process. The obvious ones: deep discharge, heat exposure, skipping maintenance, poor storage, unbalanced packs, ignoring BMS alerts. And the good news is that most of these issues are preventable, right? with a little bit of care of attention, we can prevent them. We can easily come up with the correct charging set. Now, how EPEVER contributes these issues, how EPEVER looks into aging, how EPEVER looks into these problems, and how EPEVER contributes to solve those issues, essentially. Actually, here we'll try to connect these advanced EPEVER solutions directly to the anti-aging principles. So first of all, the full lithium lineup, that's how we call it. So from small capacity packs to rack-mounted ESS modules, it directly addresses undersizing mistakes, and by offering the right size and configuration for every application, we reduce the risk of deep over discharge, protecting the life cycle of the batteries. And then we have the smart battery management systems. It's a direct safeguard against poor temperature management or overcharging, over discharging. And with real-time monitoring of voltage, current, temperature, cell balance, we do it all to prevent the thermal stress and imbalance that accelerates the aging. And this design ensures your system operates within the safe depths of discharge limits, mitigating sulfation and lead acid, and lithium plating and lithium cells, shall we say. In short, kind of an anti-aging system built in the batteries. Flexibility in form factors, wall or rack or floor shading means optimal placement and proper ventilation, which we know prevents the heat buildup and slows degradation. And our long life and reliability uh, promises. We use A-grade life Pure4 cells. We deliver 4,000 to 6,000 life cycles at 80% depth of discharge. And this is a direct counter to rapid cycling wear and deep over discharge damage. And by maintaining a comfortable working depth, we slow down the chemical breakdown. So finally, we also have the global safety compliance. You name it, CE, IEC, ROHS, and UN 38.3 certifications. These all confirm resilience against overheating, electrical faults, you name it, and unsafe environments. And these certifications, ensure that our batteries are tested against those phenomena. So we have valve-mounted systems with higher capacities as well. We have floor standing systems. These units are stackable and stable, designed for industrial and microgrid use. Mismatched components and improper placement could cause inefficiencies and heat retention in these systems. So at the heart, in general, we are combining intelligent design, certified safety, operational discipline, and we try to contribute to avoid common mistakes we outlined earlier, keeping our batteries in their prime for longer, protecting your investment, and maintaining dependable energy delivery. So, with that, okay, great. Thank you, everybody, and wish you a nice day.